I would like to introduce our final speaker. We saved the best for last. So we have Dr. Jin-Sung Kim from NVIDIA. He is an experimental quantum physicist by training, and he's currently responsible for developing the ecosystem of the NVIDIA quantum platform. He manages technical collaborations and external partnerships, and he ensures that the user base consisting of domain scientists, developers, physicists, and enterprise users are enabled with the best tools for developing useful quantum applications. He received his PhD from Princeton University with Professor Stephen Leone, studying electron spins confined in metal oxide silicon quantum dots. And so without further ado, please take it away, Dr. Jin-Sung.
All right, thanks, Tony, for the introduction. It's really nice to be here and speaking to you all, and for the opportunity to tell you all about some of the work that we're doing at NVIDIA within the quantum computing group. Thanks for the my LinkedIn intro, Cody. But yeah, I've been at NVIDIA for a little over 3 years now. I used to be a research scientist at IBM, working on the computers there. As Cody said, I did the PhD at Princeton, so trained as an experimentalist, looking at spins and quantum dots prior to that. So I'll be very happy to tell you some of the things that we're doing at NVIDIA. Just a little bit of housekeeping. So the way that the morning session is going to be structured is I'll give a bit of a talk on some of the things that we're working on. And then the next 2 hours, we'll do a bit of a hands-on demonstration. So we have a bunch of GPUs allocated for you folks. I think some of you are running into some sort of login loop issue. We'll get that resolved. We'll take care of it during the break, so it should be no problem. But yeah, so let's jump right into it. So to motivate some of the work that we've been doing in quantum at NVIDIA, it's really instructive to just look at some of the biggest results that have been happening in quantum in the past year or so. So it's been a really incredible year of breakthroughs in quantum across a variety of different qubit architectures, both in hardware, software, and in algorithms. So just highlighting a couple of them here. They are, of course, too many to list fully on one slide, but I think in the past year, there have been kind of 2 major categories of major breakthroughs. The first being in very real, tangible demonstrations of quantum error correction on real hardware across different quantum architectures. So, of course, Google with their massive Willow announcement last year, Square with their 48 logical qubit announcement a little bit before that, but also with Quantinuum and Inflection, both with logical qubit demonstrations and a couple more that I haven't mentioned here, including from Adam, Alison Bob, and Lord Quantique. So it's pretty evident that the industry is beginning to converge their efforts on quantum error correction in a very serious way and make real progress towards this. And this is a very serious focus for us as well. The second category of advancements is kind of in novel architectures. So quantum hardware that has the potential to really drastically reduce the overheads necessary for quantum error correction, or otherwise have the potential to enable much higher scalability in a useful quantum computer. So seeing recent developments from folks like Microsoft with their progress towards Majorana, which is a pretty exotic qubit within space. AWS with their CAT qubits, PsiQuantum and Xanadu both releasing architectures for modular photonic systems made from kind of industry standard components that can nominally scale out to an entire data center. So what we'd love to see here is that there's so many different modalities of serious efforts and progress being made, and many different architectures and pathways being explored that can all make quantum computing successful in the future. Okay, so how does NVIDIA fit into all of this? Well, we are not building our own quantum hardware or qubits or quantum computers ourselves. I've already listed a bunch of companies who are very, very good at that already. But what we are good at, and what we have a lot of deep expertise in, is building heterogeneous compute systems with new types of accelerators, networking them together, scaling them out, and making them into useful scientific tools that are easy to use. So taking a step back, we can actually draw a lot of learnings from the development of the GPU and how it scaled to be kind of the engine of modern computing and AI today. And we can draw some parallels to how we're thinking about quantum computing today. So back in the 90s, our company was founded. We developed the GPU to basically do one thing, to develop graphics. And it was a new type of accelerator, and it was a pretty specialized piece of hardware that used a pretty specific way to program it. So you basically programmed it in the language of shader APIs or the language of graphics. Shortly after, in the early 2000s, some very smart researchers out of Stanford figured out that you can basically recast quantum chemistry and molecular dynamics simulations into this language of parallel processing and graphics. And you can basically trick a GPU into being like a small supercomputer. The problem with this was that it was very painful to do this translation from the language of quantum chemistry to the language of graphics using shader APIs. So what our company did was develop this framework called CUDA. And so CUDA is kind of the framework that ultimately allowed developers and researchers and scientists to leverage the GPU as kind of a compute machine. So it was a much easier way to compute to develop applications and programs at scale on GPUs, and ultimately led to some of the other developments down the line. So notably, machine learning. So in around 2011, some pretty famous now researchers at University of Toronto, Jeffrey Hinton, Ilya Sutskever, Alex Krizhevsky, you may recognize some of these names as like the founders and former CTO of OpenAI. Well, they figured out that you can use CUDA and GPUs to do deep learning really well. So this was kind of the thing that unlocked deep learning and machine learning and showed kind of the world that GPUs and parallelized computing is really useful for things like deep learning. And ultimately, this led to the advancements at OpenAI, kind of the Gen AI engines that we know today, and all of that good stuff. So the rest is kind of history. We see a lot of similarities between the ability to program a GPU supercomputer, and it's a very similar picture to how we see quantum computing today. So there's a lot of learnings that we can take from the development of the GPU that we can apply for quantum computing as well. And so what does this actually look like for quantum computing? So what we think this will look like, and what a lot of other folks think this will look like as well, is that useful quantum computing in the future is going to be a quantum computer next to a supercomputer. And this is actually echoed by our CEO over the weekend when he made the prediction that every supercomputer will have a quantum computer next to it in the future. So quantum computing is not going to do everything themselves, but will be, of course, a critical part of solving very important problems that we can't solve today with CPUs or GPUs. But on the flip side, supercomputers are actually very useful tools for making advancements in quantum computing today. And so what we think is that this kind of hybrid interaction, the hybrid nature, will be very useful for workloads with the quantum computer in the future, whether that's hybrid algorithms, pre and post processing, calibration, control, and error correction. So we have to really carefully consider what a fully integrated system is, both from the low-level systems integration to kind of the high-level methods for developing applications. So this vision is our North Star. We call it the accelerated quantum supercomputer. This is what we're trying to help the entire ecosystem build towards. So this is connecting quantum processors of all architectures to AI supercomputers for the purposes of developing hybrid applications, leveraging AI methods for quantum, developing the low-level and low-latency connections between the quantum processor and the GPU, all the way up to high-level libraries for enabling the end user, who may not be a quantum physicist, to program the system in this kind of the similar way that they would program just in a normal computer. Okay, so at the heart of our platform is CUDA-Q. CUDA-Q is our software platform and programming model for quantum computing. It's open source and qubit agnostic. At NVIDIA, we like to use the acronym SOL, so that means speed of light. So the fastest or the cheapest or most effective way that you can do something limited by the laws of physics. So CUDA was built to be our speed of light software for developing applications on the GPU or a GPU supercomputer. And in a similar way, CUDA-Q is our speed of light software for programming the GPU, integrating it into the GPU ecosystem, and ultimately, hopefully making quantum successful overall. So a big part of this is the enablement and integration with the entire ecosystem. So we want end users to be able to program a single source code flexibly and easily leverage different types of quantum processors or simulators, with also the ability to write your code once and not have to rewrite it every time you want to run it on a new quantum architecture. So we want users to be able to tap into also a broader set of users to access their platforms, meaning our quantum partners, So this folds in kind of the ecosystem of HPC users and GPU and AI developers into kind of the ecosystem of quantum. So what this also enables is quantum users to leverage the interoperability of CUDA-Q to tap into modern AI and HPC applications. So there's this kind of virtuous cycle for enabling more users to easily access quantum platforms, which then kind of drives the innovation and development on the platform side. So all the logos that you see here on the right are quantum processors that you can access today with CUDA-Q, with several more not listed here that are in the process of integrating. And you'll notice that basically every modality of quantum hardware is represented here, as well as both digital and analog processors, which we both support. Also highlighted here is our integration with AWS Bracket. And so there's a number of different quantum processors hosted on AWS that you can also access via CUDA-Q on their platform. They have a native integration with CUDA-Q in their environment today. So in addition to quantum hardware, we've also, our integrations with quantum hardware partners, we've also developed very powerful simulation tools for quantum. So for speed of light simulation, we've developed a set of libraries called cuQuantum, which are extremely performant and powerful tools for developing algorithms and applications and understanding kind of scaling behavior of quantum algorithms. So for us and our partners, simulation is a really nice complementary tool for quantum computing. We don't consider it as a competitive tool, but instead it's a tool to enable and further research within quantum computing. And there's many reasons to leverage simulators. Obviously, many of our partners and users like to just use them to prototype algorithms before they run them on real quantum hardware. Others like to use it to kind of controllably understand the effects of noise on their algorithms and to study error mitigation techniques. And others use it to help them design and develop better control techniques and refine their parameter space for developing novel quantum hardware. So simulation is a very important tool in our toolkit and close to our hearts at NVIDIA. There's actually, back in the 90s, simulation actually saved the company. So there's a time when we were trying to develop one of the first GPUs that we're sending to market. The company had very little money at this point, very little runway, and we didn't have enough time to actually produce any prototypes of the first GPU system, so the NV1 system. So how do you test and troubleshoot a system when you don't have access to the actual hardware yet? So what you do is you build a simulator. So we built a simulator back in the 90s that actually simulated the outputs of the GPU that was under development. Successfully tested it through that pipeline, brought to market, and the company survived to this day. So we do this still to this day. We use simulators for every next generation of GPU. We use AI techniques for designing every next generation of GPU. So it's a very powerful tool that we use to this day for our own workloads. One last use case for simulation that we found as a critical tool for kind of modern quantum error correction workloads today is the ability to generate synthetic data for training AI models for quantum. So this is very similar to the way that we use simulation to train robots and self-driving cars. I'll talk more about that in a couple of slides. This is pretty recent work of ours that we did in collaboration with Quora. One thing that's important to mention here is that we release our simulation acceleration libraries independently from CUDA-Q. So every other framework within the quantum ecosystem can also pick up our acceleration capabilities and integrate them into their frameworks. They can leverage them to access high performance simulation for their workloads. So if you have your own favorite framework, like Cirq, Pennylean, or Qiskit, or if you're developing your own codes, you can also pick up these acceleration APIs and integrate them into your own codes. So really trying to enable the entire ecosystem to pick up and leverage GPUs to accelerate their work. Okay, so kind of on the opposite ends of the stack, we have a new set of libraries called CUDA-QX. So these are high-level libraries for accelerating applications development. So for CUDA, libraries have been a big part of making it easy to program applications for the GPU. There's many examples of this. In particular, one library called QDNN allows people to just build deep neural networks at scale on GPUs, so people don't have to worry about like the low-level nitty-gritty designing a neural network architecture on a GPU. It's very similar for quantum computing. We really want folks to be able to streamline their applications development and streamline their explorations into things like quantum error correction. So what we've released in the past couple of months is a new library called QDQ. So these are a set of tools. It's an integration with STIM for those of you who are familiar with that for generating Clifford circuits, and then it has a few pre-baked codes and decoders that you can use to explore kind of accelerating these workflows on GPU. And it's flexible enough that you can also bring your own decoders and plug them into your own workflows. The second library here is called CUDA-Q solvers. There's a set of primitives for designing other quantum applications, in particular, things within the quantum chemistry domain. So there's primitives and APIs for developing, for doing things like Hamiltonian transformations, mapping them onto qubits. There's an integration with ISCF, among other things. So these are the first two libraries that we're starting with. There will be more in the future, but we think this is a very good starting point. At the very bottom of the stack, we have a system and reference architecture called DGX Quantum. So I mentioned before that building a tightly coupled supercomputer and QPU system will require low latency methods and a really thoughtful connection. So what we've developed is a microsecond latency system that directly couples the GPU to the quantum control hardware, a system built by quantum machines. So this is kind of the first iteration of that. It's the first system of its kind. It won't be the last, where we have a direct coupling from a GPU to a QPU. And we can start to explore workflows leveraging GPUs for things like real-time calibration, control schemes, and start to do investigations into even things like real-time error correction decoding. So this is our overall platform. It's open source and available to use. We built the whole platform, but we distribute it in a disaggregated way. So you can either take the whole stack and use it if it's for you, or you can just pick and choose what levels of the stack are useful to you. You can integrate into your own codes. It's very flexible, so you can take the parts that are most useful to you. And so as a platform company, our success is directly dictated by the success of our partners. So when our partners succeed, we succeed. So we're really happy and proud to be able to partner really broadly across the entire quantum ecosystem. We have a pretty amazing ability and privilege to be able to work with nearly every quantum company, whether it's QPU builders, some of the largest companies in the world, software startups, research centers, supercomputing centers, and universities. So really, every group working on quantum can use some part of their stack to accelerate their workflows. We work with basically everyone in the space to try and enable their work. So we're very proud of this slide and the partnerships that we have today. So how do we get to where we are today, to where we want to be in the future? So this vision of the accelerated quantum supercomputer. So to realize this, there's a number of different challenges ahead that we think are broadly the most important things that we need to address to take us from kind of the NISQI qubit systems that we have today to this vision of the fault-tolerant accelerated quantum supercomputer. And so the first thing is, of course, we need to build better quantum hardware. We need to build better quantum processors, need better improved scale, fidelity, connectivity, reliability, gate fidelities, et cetera, et cetera. The second thing is we need to build better algorithms and applications. So the question is, how do we get more compute from less resources for things like near-term algorithms? Can we reduce the number of operations that we need to achieve something useful? For long-term things, can we implement error correction codes or error mitigation techniques to give us better results and give us lower overheads in terms of physical qubit counts and things like that? The third thing is scaling quantum error correction. So there's a lot of things that we need to do for quantum error correction. It's not a trivial problem whatsoever or a solved problem whatsoever. So really to get to the scale that we need for a fully fault-tolerant quantum computer that can do something that we can't do today, we need many, many more qubits. We need to understand how to couple these things to HPC systems doing the decoding at large distant quantum error correction codes is extremely non-trivial. It's an open research question, how best do it. How do we do this in real time? How do we couple it to a real quantum computer and basically have all of it work without any of it falling apart? So there's a couple of major challenges that have kind of guided our strategy and the things that we're thinking about today and kind of the tools that we're trying to develop for the ecosystem. So starting with better quantum hardware, we of course need better qubits with longer coherence times, better gate and readout fidelities. So a lot of this work is very deep engineering and material science work, but simulation is actually a very powerful tool that can help design better quantum hardware. So one of the collaborations that we announced last year towards this was with the Google Quantum AI team, where we helped develop a simulation library for quantum dynamic simulations, so accelerating this by orders of magnitude, being able to scale it out on multiple GPUs for some really, really nice performance, making possible simulations that weren't possible before. And so this is a library called CUDA-Q Dynamics. We're going to actually be able to play with this later today. We have a couple of notebooks set up. We have a bunch of GPUs allocated so that you can all get your hands dirty with CUDA-Q Dynamics. And so, as I'm sure everyone here today knows, one of the biggest issues in quantum hardware is how to deal with and mitigate noise. So in practice, we can do a finite number of operations on the circuit before our information is lost, usually on the order of hundreds or maybe thousands before we completely decohere. And of course, this number continues to get better every year due to the great work that experimentalists and the hardware builders are doing every year. But understanding the sources of decoherence and other kind of coherent noise sources and things like crosstalk is actually really fundamental to understanding how we can address it and build better devices and design better devices. So to kind of break it down a little bit, if we have a noise source, it's actually really helpful to understand whether it's a coherent noise source or a decoherent noise source. So is the error repeatable or is it not repeatable? So if it's repeatable, there's control methods that we can throw at it. We can design better pulse sequences to cancel out things like crosstalk terms, unwanted quantum interactions. But if it's incoherent, we need to figure out what the source of the decoherence is. So this can be a difficult material science problem, but simulation can actually help here by modeling things like other two-level systems in the substrate or other spins in the substrate that are interacting with the system. And the third case is when the results of an experiment don't match the predictions of theory. So it turns out that doing some pretty hefty numerical computations can actually help resolve some of these problems when the theory doesn't match the experiment. So yeah, simulation is pretty useful for each of these cases. And so what we'd like to do is provide researchers just another tool in their toolbox for them to accelerate their understanding of what's happening in the actual physical system. So in this case, when we're talking about simulations, I'm talking about dynamic simulations or the simulation of open quantum systems, as opposed to the more typical circuit simulations. So instead of thinking about logical or noisy qubits in a state vector, we can take a bit of a closer look and treat them as kind of arbitrary quantum objects that are not depending, not just restricted to two levels. We can consider their full interactions with the external world. We can consider their interactions with control pulses and each other, as well as noise and dissipation. We can use these simulations to kind of peel back the onion for kind of controllably examining different noise sources and design around them. And we can do this iteratively and to help mitigate noise sources and kind of ideally speed up the cycle time for the next cycle for fab cycle for devices. Okay. So dynamic simulations, very similar to other quantum simulation methods. It's unsurprisingly a very computationally expensive workload, but there's a bunch of different optimizations that we can build in and a lot of structure and sparsity that we can take advantage of. So what we're showing here is a benchmark of simulating a transpond resonator and Purcell filter system. Pretty high numbers of levels for each, so 64, 256, and 4 levels respectively. And we're using the Qiskit dynamic simulator just to do kind of a single time step benchmark on a CPU. And so a single time step on this on CPU is taking about 44 minutes to run. So if you want to simulate many qubits or a system this large, it's pretty difficult to do this in a realistic time scale. And much less if you want to look at multiple different qubit parameters or cycle through and try to optimize the system, it's very difficult. So it's pretty prohibitive to actually run on CPU today. But with CUDA-Q dynamics and running this on a DGX H100, we're able to get this single time step down to less than a second. So this is about a 10,000 increase in speedup for a single time step from the hardware and the software. So really, the impact here is that it's nearly impossible to run large scale simulations of these type on CPU. It's pretty prohibitively expensive. And so what this ability enables us to do is to really start to probe systems that we couldn't probe before. So this has been released in CUDA-Q as full solvers, so you can just define your Hamiltonian. I'm going to walk you exactly through how to do this later. You put in your time schedule, you call a single API, and you run the simulation. And you can use a variety of different custom solvers for this. I also want to point out that we've also released the building blocks for accelerating these types of simulations in cuQuantum, so that other frameworks, for example, Qiskit Dynamics, Qtip, Dynamics with a Q, can also pick up the same acceleration APIs, and they can also experience the same level of acceleration. So this is not something that's exclusive to CUDA-Q, but we also release the API so that everyone else in the ecosystem can also pick up the acceleration APIs. Yeah, and we're actually working with some of the other frameworks to help them integrate these APIs today. So we're trying to enable the entire ecosystem with this. This is just another example of how we build a full stack, but we distribute it in a disaggregated way. So if you want to use your favorite framework, or if you have custom codes or internal codes that you want to accelerate, you can just pick up the right APIs and accelerate them. Okay, let's switch gears a little bit and talk about some of the work that we're doing in the algorithms and application space. So this is a major research topic among folks in the field. So I'll just focus in on just a couple of works that we've been working on. So this first workflow is a project with IonQ, AWS, and AstraZeneca. This is an auxiliary field quantum Monte Carlo method, or AFQMC. And it's towards developing better processes for designing small molecule drugs. So this is a really nice example of what a truly hybrid end-to-end application looks like. So there's a lot of instances when people talk about hybrid in the context of quantum computing, and really they're just using the classical computer to do some sort of optimization step. But there's a lot of more power and processing that can be done on the classical HPC side than just doing an optimization step. So in reality, for this case, you have to do a ton of post-processing for these workloads to give you anything meaningful. So what's happening here is you prepare a couple of trial states on the IonQ device. You do some tomography afterwards, and then you have to compute classically the overlap between kind of these trial states. And that's a pretty massive GPU intensive workload that we can speed up pretty well. So this workload used about 1,000 GPUs on AWS to do the post-processing, and they saw about a 20x increase in speed up in this end-to-end workflow. So a really, really nice example of using a really hybrid end-to-end workflow using GPUs to do the post-processing.
I interrupt?
Yeah.
Online. So when someone is asking, could you comment on the acceleration we could get with only a desktop GPU, a RTX 4060, for example? Yeah.
So you're going to get pretty good speedups on the desktop GPUs. Our software runs on all of our architectures. So of course, you're going to get the best performance on a server grade GPU, but you're still going to see pretty good performance on kind of a consumer grade GPU. So depending on the workload, we've seen orders of magnitude increase in performance on the server grade GPU, so the H100s or the B200s. But on an RTX, you'll see a pretty substantial, probably up to a single order of magnitude increase in performance. I should also say that this is dependent on the problem size. So GPUs really shine for big problems. So you don't want to be running something on a GPU for a tiny little toy problem. You probably won't see a speed up. So it's fine to just use your CPU for that. But once you start getting to big problems, the GPU really shines. Okay. So this second example of work is done in collaboration with the research team at HPE, so led by Masumo Seni. So one of their main research interests is to figure out what a distributed quantum computing system looks like integrated with the supercomputer. So this is very similar to how we think about the accelerated quantum supercomputer. So in the future, it may be the case that a quantum system needs to be distributed. It may be really difficult to put all 1 million physical qubits in the same quantum node. So it may be the case that we need to distribute this across multiple quantum processors and then network them together, and then probably do some sort of post-processing to stitch back the entanglement. So in collaboration with our applications team, we've developed an adaptive circuit knitting technique. So this is a way of strategically cutting up a circuit into subcircuits, distributing that onto different nodes, and then stitching it back together. And it turns out if you're strategic about where you make these cuts, because the overhead is exponential, but if you're smart about where you make the cuts, you can actually substantially lower these overheads. So with this kind of adaptive circuit knitting technique, we're able to get a couple of orders of magnitude fewer overhead in the sampling for circuit knitting. Okay, this third example of work was recent work from the research team in Taiwan at NCHC. So this is studying the scaling behavior of quantum machine learning workloads. And this is going to be really difficult to extrapolate on quantum hardware with a small number of qubits and a small number of parameters. And really, quantum machine learning, it's a bit of an open research question, when and where and how it can be potentially useful for speeding up machine learning workflows. So they used our tensor network library and QDW to simulate a quantum support vector machine to simulate a 784 qubit system to really start to understand the scaling behavior of this method. So this is really nice work because you can use some pretty advanced simulation methods to start to probe a qubit regime that's really difficult to probe otherwise, and to kind of understand the scaling behaviors of your algorithms. And I should also mention that over the weekend, NCHC announced a new GPU supercomputer that they're going to be dedicating for their work in quantum and AI. So really exciting to see that work continuing. There's going to be a new supercomputer for these types of workloads in Taiwan. So for all of these examples, we're showing how hybrid systems and how accelerated computing kind of work together to achieve the aims here. Yeah, question.
For the AFQMC project, is there a paper out yet?
There's a technical blog. I think the paper is still being written.
Thanks.
Yeah, the previous AFQMC technique, there's an archive paper on that technique exactly, and then I don't think the details of post-processing have been released yet.
Thank you.
Okay, so let's talk about quantum error correction. This is kind of the third thing that it's one of the most well-studied aspect of achieving a quantum advantage in the future. So very likely we're going to have a fully component quantum computer to do something useful on a quantum computer. So if we look at kind of state-of-the-art gate fidelities, we're seeing around 99.9 around there, 2 qubit gate fidelities for kind of best systems. But the estimates for a real quantum algorithm and achieving a useful calculation, we probably need much better logical qubit error rates. And so really the only way to get to the projected error rates, many more orders of magnitude of error accuracy, is to do error correction. So of course, what this looks like is we do a bunch of measurements on the quantum computer, extract a bunch of syndrome measurements, feed that into a decoder on the classical side, and then feed the corrections back to the quantum processor. And you have to do this, with pretty low latency and basically on the time scale of how fast the quantum processor is operating, because otherwise you incur this exponential backlog of errors, and that makes everything fall apart. Yes. Oh, okay, yeah. I don't know how to.
Cody was there? No, I want to come up here. No, Cody was handling that, I think.
Okay. Yeah, I'll wait for Cody to raise any questions from the chat. So if you look at a real quantum computing workflow, we're just taking some numbers from this Google paper from 2019 on how to factor to break RSA with Shor's algorithm. Just pulling a couple rough numbers from this, you can see that you need of order millions of qubits, physical qubits, but you only have something like thousands or tens of thousands of logical qubits. And so what this means is the majority of the work that's being done is just doing error correction cycles. So that producing 100 terabytes of data per second that you need to process. So the reality of the situation is that a useful quantum computer is mostly doing quantum error correction and a little bit of computation. So I think this point gets a little bit varied when we talk about fault tolerance, but this is something that's really important to keep in mind and something that we're considering deeply. So when we're thinking about the classical compute side of a useful quantum error correction workflow, there's kind of two axes that are the most important here. There's the code distance, or how robust your code is to errors and how much you can suppress your errors. And then there's also the decoding time. This is how quickly you can figure out what the correct error that's occurred on your system.
I have a question.
Yeah.
In terms of material and hardware, which have proven to reduce error rates the best and prolong coherence times in general?
Yeah, so I think probably the best quantum error correction results today are probably from the Google team, where they see like a lambda error suppression factor of 2 every time they increase the code distance. I'm not aware of experimental results that have a higher error suppression rate than that. Okay, so we want to keep the code distances large to suppress errors. People estimate that we probably need to get to like a distance 30 code to achieve realistic logical error rates. But we also want the decoding time to be of the order of how fast the quantum computer is operating. So this is a pretty difficult trade-off to deal with. And so with kind of industry standard decoders today, the bigger your decoding, your code distance gets, the more time it takes to decode what the error is. So there's these kind of trade-offs, and generally this is a kind of a quadratic, scaling time. But there's maybe ways to speed this up, and maybe there's ways that we can speed this up to the point where we can actually get to practical quantum error correction. So one thing that's possible is to just parallelize your decoding. So there's methods here that we can think about. And this can oftentimes give a pretty good speed up. So for smaller codes, we probably won't see as much of the speed up because the codes are small, so the computation's not that great. And a part of the reason why people are generally haven't used GPUs for recent error correction experiments. But for much larger codes, the compute needed for decoding increases. So the benefits of parallelization and the benefits of using a GPU system become more apparent. So it's a big open research question on how to successfully implement this. So this is something that we've been working on. And so one of the first results that we've shown in the past couple of months is this new decoder in our QEC library. So this is a new parallelized accelerated decoder accelerating BPOSD, so belief propagation, which is pretty popular method of decoding quantum LDPC codes. And to our knowledge, this is the first GPU accelerated decoder that's publicly available. We're seeing really nice performance metrics here. So about a 30x increase in performance over kind of the CPU implementations. And then the other thing that we can do is batch this, so we can do multiple decoding rounds simultaneously on a single GPU, and then this gives us another 20 to 40x increase in throughput. So this is a really promising start for kind of attacking this decoding problem just through pure parallelization. The other thing that we can think about is using AI methods for decoding. And so this is a really interesting research thrust for us. So the question is, what's the benefit of using AI methods for this? So a lot of people are using AI for a lot of things. A lot of people are using it as kind of a way to hype up their, or just you guys know anything. So, but there's very real reasons to use AI for these types of workflows. So the main thing is that if you can transform the decoding problem into an AI inference problem, you can actually just front load a bunch of the computation. So what I mean by this is there's two major components of an AI workload. There's the training of a model, so you can throw a bunch of data and a bunch of computation and train this model to make some predictions. And then you run inference through it, and this is when you actually are solving some sort of problem. And it turns out the inference part is actually, it can be done pretty efficiently, and it actually scales pretty well. So once you have your trained model and you front load all your computation, it may actually be a pretty useful thing to use AI to just run inference, and the scaling benefits seem to indicate that this may be a viable way to do decoding. So definitely exploratory work, but we have some initial results to show here. Yeah.
I think AI is kind of a meaningless term at this point. You mean like machine learning or transformers or?
Yeah, so this is a transformer model. We like to have a pretty broad umbrella of what constitutes AI, but this is a transformer model. And I'll talk about the details a little bit. Okay, so we built this neural network decoder in collaboration with Quora. There's also very nice work out of the Google group with their alpha qubit decoder. So some already fantastic existing work. So we worked with Quora to train a model using synthetic data with some realistic noise sources from their processor. And we got some really nice preliminary results for just a small system. This is the t=3 code. But what's really exciting here is we were able to get better results than their previous decoder, which was using maximum likelihood. And so in terms of accuracy, we're doing a little bit better than their previous decoder. But the really interesting thing is that the decoding time was about 50 times faster. So it's on the order of a millisecond. So this starts to get into the regime where real-time decoding with an AI decoder may actually be possible for something like a neutral atom system. So definitely a lot of work to do still, but this is a really good start. In the future, we want to get to much larger codes, but there's a couple of things that we need to figure out. So for larger codes, we need a lot more training data. We probably want to fine tune the model on some real GPU data, but we can do that. There's methods of fine tuning a model afterwards. And then we really want to be able to deploy this for real-time decoding. For the first thing, we've actually made some really nice progress towards this in just generating a ton of synthetic data. So what we can do is, we can speed this process up on GPUs. We can inject some pretty specific noise channels depending on what the quantum system is, and then we can do some pretty clever sampling techniques so that we can pump out just a massive number of shots and still have a pretty good representation of the underlying statistical distribution. So running this on a portion of an H100 supercomputer, we're able to emulate an 85 qubit system using our tensor network library and generate 1 million shots in about 6 hours. So this is a really, really nice platform for generating a bunch of data for training these models. For a more moderately sized system, this 35 qubit system, we're able to generate 1 trillion shots in just about 2 hours. So this is a really nice platform and pipeline for generating synthetic data for training these types of models. And this is a very similar picture to how people train models for things like self-driving cars or robotics, where getting that data is actually very expensive. You need a real driver, real data. So just doing the simulation is a much more streamlined way of getting some of this done.
There's a online question.
Yes.
How do you integrate quantum-based homomorphic computation for decoding encrypted data?
What was the first part?
How do you integrate quantum-based homomorphic computation for decoding encrypted data?
I don't know what quandle means.
All right, no worries.
Okay, I can circle back to that.
Yeah.
All right, and so we developed this pipeline. This is trained with an open source, another NVIDIA framework. This is a physics AI framework called Physics Nemo, and so this is also open. This is part of another open source package. So there's this really nice pipeline. Okay, so I'm going to speed through the last couple of slides here. So we want to think about how to implement, real-time error correction, and it turns out, the way that we connect to quantum processors today is largely, over the cloud through something like a REST API. But what we really want to move towards is this more tightly integrated picture. So where you have a host device that's controlling multiple different CPUs, GPUs, and quantum processors. And within the quantum processor, you have, a pretty complicated picture that looks something like this. Where you have a control driver, and you probably also want to access a bunch of classical devices, so accessing GPUs to do things like decoding or real-time controller calibration routines. So what this looks like is, you may need a single GPU, you may need an entire node, you may need the entire supercomputer. So this is really what we mean when we say CUDA-Q is the programming model for the accelerated quantum supercomputer. We can pull on a lot of the existing GPU and compiler architectures that have been built out for the GPU supercomputer and make the integration into the existing architecture much more seamless using CUDA-Q. And so we're doing this in open source and GPU agnostic way. I want to announce, well, this was announced a couple of months ago, but the first quantum groups are receiving these systems basically this week and the week after. But a number of them, so this is our system for low latency connection between a GPU and a QPU system. Among this group is CUDAQ, which is a spin qubit company out of Australia, as well as Will Oliver's group at MIT. So we're really excited to see what these folks will be able to do with the system. And a lot of the things that I've talked about have been kind of forward-looking, but I do want to mention that this model of the accelerated quantum supercomputer is already starting to happen at supercomputing centers all around the world. So there's a number of different supercomputing centers that are doing this already. Over the weekend, AIST in Japan just did their ribbon cutting ceremony, so they have a 2,000 GPU supercomputer dedicated for quantum computing research. They're coupling it to a bunch of different quantum computers. The same thing is happening all over the world. And in March, we also announced that we're joining suit. So NVIDIA is doubling down on our efforts towards this picture of the accelerated quantum supercomputer. And part of this is a new research center based in Boston, where the centerpiece is this NVL 72 system. So it's about 500 Grace Blackwell chips with more than 500 Blackwell GPUs. We're partnering with Quera, Quantinuum Quantum Machines, as well as groups from Harvard and MIT to really push the frontier of quantum computing, the three ways that I talked about before. Okay, with that, I'd like to thank you for your time. I'll leave a couple of links up here. There's a quick start guide to getting started with CUDA-Q. We have an NVIDIA academic grant program, so if your PI is interested, you can apply to this. It's a short application, but you can get your own GPU for doing quantum computing research. You can also get a ton of cloud credits depending on your applications. So it's a really nice way to get access to GPUs. And there's some also very nice research resources on AWS where if you have research projects, you can get cloud compute time on AWS. And they have a native CUDA-Q implementation and environment that you can just leverage. Okay, feel free to reach out to me. My email is up there if you have any further questions or if you have any questions about this program. So I'd like to thank you for listening to my talk and taking questions.
So we're talking about heterogeneous computing, including QPUs in this kind of situation. And when you were talking about sort of the architectures that you're using, the QPU always, like there's all the GPUs you have, there's the QPU, and then there's a host device sitting between them, right? Do you foresee eliminating that with like a direct interconnect between the QPU and GPUs directly?
Yeah, so we found for the fastest connection, you generally want to skip the host device.
Yeah.
And so there's ways to, load things directly onto the GPU memory and, have a persistent kernel so that, ideally you can send, syndrome data from the controller directly into GPU memory. Yeah. So we're thinking about things like that.
So the how many milliseconds of latency, however many milliseconds you mentioned, that's still through the host device?
So for
is that just simulation?
The quantum machines DGX quantum system, we're seeing a 4 microsecond round trip latency. So this is actually going straight to the GPU.
Okay. Also, the quantum dynamics part, is that also multi-GPU?
Yes. Yep. So the demo that we did with the Google team, we used about 1,000 H100 GPUs for a pretty massive simulation. Okay, you've got it. Just correct. This is okay, can you send that to me? Okay, super. Okay. So I think let's take a 10-minute break. If you haven't already signed up for the DLI platform, I'm going to put instructions on the board, but I'm going to update them because I think a few people were having some issues logging on. But we'll have some updated instructions. we're going to have some fun playing with some GPUs. We have a bunch allocated on the cloud, so I think everyone's going to get, I think an A100, you know?
I didn't know, but probably at least.
Yeah, at least an A100, maybe an H100. But we're going to do, I'll just walk you through, some typical quantum systems that are of interest. And hopefully this will give you, the building blocks to do your own simulations and kind of explore your own purposes.
This is not familiar with 800, 800, are they just throw a lot of the GB200?
Yeah, sorry. I should talk a little bit about kind of the server grade GPUs. So
Thank you.
so these are kind of so the most recent GPU generation that you can get today is the Grace Blackwell. So Grace is the CPU, the Blackwell is the GPU. They come in a couple of different configurations, but the interesting thing here is that you can have a shared coherent memory. So the CPU can see things that are happening on GPU and vice versa. And you can pull the memory and do things with very little latency. And then to do much bigger computations, you can network all of these things together and pool the memory. So you can treat it as one giant GPU with terabytes of memory and do kind of coordinated workloads happening. And then the older generations are the Hopper and then the Ampere.
If anybody has questions on the hardware.
Oh yeah, Mark, do you want to introduce yourself and Alex?
Sure. My name is Mark Skinner. I'm a solution architect. I drove up from San Diego this morning to talk to all of you folks. Thank you for being what we like to say is the focus of our company, because what you do on our equipment and the software that you develop and the software that you use that we've developed, that we're developing, is really what makes our company valuable and moves us forward. My experience is putting stuff in racks and GPUs and data centers, pooling them, finding out what is appropriate for the use case. When Jensen talked about the GB272, that's 36 72 core CPUs directly connected to 72 Blackwell latest gen GPUs, 100 and I believe 141 gigabytes, potentially 188 gigabytes per GPU in one rack. Yeah, it's 100 kilowatts of power. So that's the end goal, to get you guys in your quantum computing there. But yeah, if you have questions on hardware and what's good in a laptop or what's good in a server or in a desktop, we have a Spark that you can start doing some of this kind of work. Then come see me. And I also want to introduce Alex Steiner, who knows a lot more about the software stack than I do.
Yeah, Alex Steiner. I'm also a senior solutions architect. Went to UCLA for my master's, so back here. Let's see. Yeah, so I'm like more of an AI ML expert. So LLMs or running LLMs on GPUs, but I'm not a physicist, so I can help a little bit. But I don't.
So hopefully among the three of us, we can help answer any questions that pop up. Okay, so what I'm going to do is, Mark, can I get those updated, that updated link?
Yeah, put it in Slack. Yeah, that is easier. The Slack email that you repost for me.
So which
Actually, do this. Get rid of the join, the slash join there, because that's what the problem was.
just like that.
Yeah, and if they have that too, and if they have struggles, they can go to just edit your real name. Solid. Yeah. All right, so if any of you were struggling using the first link that said /join, they told us on the back end that it was confusing people. So if you go to that first website and you click the join button, that will help. If that doesn't work, go directly to the second link there. It just says nvidia.com/en-us-training.
The link said that
Yeah, it has.
does not exist.
But then it redirects you in the
It's
page.
gonna redirect
So
you.
you
Redirect
just-
you. It's gonna either way. It's gonna redirect you to the second one. So you want to jump to the end like Alex did. I'm just telling you what they told me. To the second one.
Are folks able to get on?
Also, that's the link on the bottom when you eventually are asked for the.
Okay, beautiful. And then you can go ahead and start it.
Okay, to get started.
Okay, so let's take a break for 5 minutes and then we'll walk around and make sure everyone is able to get on, and then we'll get started.
My spot.
Good spot.
Good. I think I saw. Sorry. There's nothing in the floor. I guess this is just for lecture. Anybody who failed before getting in successfully? Yep. Couple of thumbs up. Good, thank you.
Oh.
Oh, you're still. Are you, yeah. Can't be reached, so thank you. All right, so click that button. And then try your credentials and then see if that takes you to the DLI page.
Yeah.
While we're taking this break, I thought I'd share a couple of websites for you. We bought a company called brev.dev. So that's a place where you can go and with a little bit of money, you can swipe a credit card and get an instance. There's also launch pads that you can play with for free. The DLI courses, some of them, like the one that you're doing now, are paid for. Some of them, a lot of them are free. You can try. Probably the most important link I want to share with you is NGC, which is our NVIDIA repo for software and models. So NGC has 800 models to play with in several different domains, and then also somewhere in the neighborhood of 450 containers. So if you wanted to do typical, Python development for AI, you would want to run PyTorch, right? Well, that's one of the most popular containers. So you would just say Docker run nvidia.nvcr.io/PyTorch. And that's the location. NGC Nancy George Charlie .nvidia.com. Enjoy those.
Well, maybe.
So the credentials. Yeah. Great. When we go to that, we get our courses done. That's great. But you don't have to. I don't believe you have to.
Moves to.
Was there a?
That's what it shows.
I just remember something in an email saying something about.
So after you create I think you requested.
You direct.
मतलब इसमें कुछ खास टेक्निकल डिटेल नहीं है इसमें फ्रैगमेंट में ओवरव्यू होता है कि कहीं ना कुछ बार
Using the first page.
मतलब बेसिकली थियरी के बारे में क्या मैसेज है बहुत लिमिट है
Just try.
You can walk. Now you're actually starting. Yeah, the email that
Yeah, that's really interesting.
But for the DLI, it's all online.
This is the embedding one. Everything should be in there, so yeah. So when you go here,
Does it say what GPU you run? That'd be cool. Yes. System.
Okay, folks, has everyone been able to get onto the platform? Any issues? Okay, great.
The GPU is an A10.
Okay, okay, so A10's
Anybody not able to get online? I think we got the last couple of people online. Good, all right. So you now.
let's see if I can get on.
Should we,
Yeah, if you don't mind just checking to see if folks can get on in the other room as well.
Ambassador and Vegas. Yeah.
What do you do here?
So when I said, is everyone able to get on? Is everyone able to get on? Okay, so go ahead and take a picture of this if you're not on the platform, and then we can start getting started. So you should have just take a picture, and then we'll manage. All right. So now, is everyone good? All right. So you should have been able to start the instance. So it should have taken you to like a splash page to start with like a play button. And is everyone on this page now? Okay, good. Let's go into advanced examples and dynamics. And then we'll just click into lab one. So we'll do this for the next, say, 40 minutes, take a little break, and then we'll do the next one for the next hour or so. Okay, can everyone see this? Okay. All right, so let's talk a little bit more specifically about CUDA-Q dynamics. So as I mentioned before, this is a high-level solver framework. Oh, okay. Yeah, if you don't mind. Okay. So has anyone here used like a circuit simulator before, or like another like quantum evolution simulator, like QTIP or like dynamics? Or okay, good. All right. So I don't need to spend too much time integrating this, but basically, what we have in CUDA-Q now is a new library called CUDA-Q Dynamics. So this is for enabling GPU accelerated simulations of the time evolution of open and closed quantum systems. So basically, dynamic simulations, for those of you who are not aware, represent how the system evolves in time. So this is really useful for studying non-idealities of the quantum system, interactions with the environment and other quantum systems. And so kind of, we like to show this picture to draw a classical analogy. So, the logic of a classical computer can be modeled using binary logic gates applied to a transistor. This is very analogous to simulating the application of solid logic gates to qubits. But this gives you no information about kind of how the devices are performing. So you really want to look at like dynamic simulations or the dynamic performance of these transistors to understand, like what are the transients, where are the voltages happening, where are the currents happening, things like that. And there's a similar picture for the quantum case. So, here's your circuit simulation. This gives you the algorithmic outputs. You can study, noisy quantum gates here as well in CUDA-Q. But to get like a real understanding of what's happening on the device, it's very useful to look at these quantum dynamic simulations. All right. So the functionality here, this is basically a one-liner in CUDA-Q. So basically, we call the evolve API. So this sets everything in motion. All we need to do is set the dimensions of the system, define your Hamiltonian, the initial state of the system. You can add any dissipation terms you want, and the time schedule. So this is also very conveniently the same programming model and API used to submit jobs to analog quantum devices. So for example, like Quera and Pascal have analog mode quantum devices. They use the exact same evolve API to program those processes. And for the simulation workloads, we have a bunch of commonly used numerical integrators already built in. So you can just kind of pick and choose if you have a favorite numerical integrator. I don't. I just use whatever the standard thing is. You may have a preference on like if you want to like RK4 or like something higher order or something like that. Okay, so in addition to kind of this higher level functionality, we provide a lower level library called Cude-Density Mat. So these are all the acceleration APIs that enable the building blocks for accelerating custom solvers and other dynamics frameworks. So if you have your own custom codes, internal codes, or if you want to use another framework like Qtip or Dynamics, these are the APIs that you can use to accelerate those codes. So just to give a little bit of intuition here, most of the time that's happening when you do these calculations is applying basically the Liouvillean operator to your quantum state. And so, generally you have a pretty large matrix that represents the Liouvillean, and just doing this massive matrix operation to update, your quantum state. That's basically the fundamental action that's happening here. And so we have APIs that do this very, very performantly on the GPU and allow you to scale it out to multiple GPUs to do strong scaling, which means you can just throw more GPUs at the same size problem to get more performance, and also weak scaling. So if you want to scale out the size of your problem and just throw more GPUs to increase the scale of the problem at hand, you can do that, and you don't really suffer a performance hit. Okay. So one thing that I should mention here is that in general, GPUs thrive on big problems, so big compute problems. So we'll see maximal speedups over CPU implementations when your Hilbert space is larger than, say, 1,000 levels. So if you take all the subsystems in your system and multiply them together, this number should be 1,000 or more for you to see like a really good speedup. For smaller systems, it's fine to use a CPU. Like you probably won't see much of a speedup using a GPU. But like I said before, it's common to see like orders of magnitude faster for these kind of, the fundamental time step execution on GPU versus CPU. So as I said before, we have multi-GPU and multi-node capabilities. So if you want to just increase the performance or increase the scale of your simulations, it's relatively straightforward to do that. Yes?
What if I have let's say 9, 10 qubit systems, it's about 1,000 levels, but I want to parallelize things a lot.
Yeah. So there's a couple of different levels of parallelization. There's parallelization in applying the Hamiltonian to your qubit states. So that can be accelerated, but there's another level of parallelization where you can just batch different jobs. Exactly. So that's kind of your embarrassingly parallelizable capability. And we have an API for that as well. Okay. So for this first example, I'm going to try to not teach any physics. And I'm going to try to just, there's people here who will do a much better job of doing that than me. But I'm going to try to use these as just examples to give you some intuition on how to use these APIs. So for the folks here, are you guys familiar with the James-Cummings Hamiltonian? Okay, great. So I don't have to do much to explain it, but I will do so for folks who are not familiar with this Hamiltonian. So this is an important theoretical model describing how basically an atom interacts with light. And so this is a pretty powerful building block for modeling and designing a lot of different architectures, including superconducting qubit systems, as well as trapped ions, things like that. It can be extended to describe a lot of the interactions in superconducting qubit systems. And then in practice, the way that you control these is, by adjusting the parameters of the light interacting with the qubit or adding additional control pulses, things like that. That is kind of the basic area. You have light confined in a resonator, and then you have some sort of two-level system inside of it, which can be, a Dresden junction, a qubit, or an atom, anything that you really want it to be. Yes.
Question. On my experience, which I had a bit of time ago, the exactness of the GPU, I found it to be giving me slurring results, especially once I would keep working with a secret. Can you comment on that?
Is this a question about like your precision?
Yeah.
Okay, yeah. So what we've heard from other research groups is that using double precision is really critical for like long time scale dynamic simulations. So that could be one thing to double check. Just what is the precision that you're using?
So it's just a mode that you check.
Yeah, you can adjust these. So generally, for these simulations, you can do double or single precision. Just double check it, because you can run into like numerical instability issues.
Would
Yeah.
you expect the same kind of acceleration for
Yeah.
both kind of?
Yeah, if you're comparing like single to single versus double to double, yeah, you'll see the same scales. I expect.
Right, and what's the differential between like what I guess is like what I'm asking is how much you're optimizing for single precision as opposed to double precision, because single precision is produced like, or mixed precision, I guess, is used a lot in ML stuff. So.
Yeah. So I understand that the trend is towards like lower precision, but for a lot of like scientific computing applications, there's still plenty of real estate for single and double precision, and there are also methods for combining lower precision. You're probably aware of like emulation. Yeah. So there isn't really a performance hit if you're looking at that. Okay. So I'm going to talk about a little bit of physics. So for the James Cummings Hamiltonian, you can decompose it into these three Hamiltonian terms. You've got your cavity, you've got your qubit, and you've got your interaction. So we can just represent these in our standard kind of operators. I'm going to we've already done the approximations that I'm sure all of you know, but basically, taking a rotating wave, dropping constant terms, et cetera, et cetera. For a full derivation, I'll refer you to some of the other people in the room. All right, so let's go ahead and get this started. Let's import the necessary packages. So basically, just import CUDA-Q. We're going to import the operators, the schedule, this integrator, the spin class is quite convenient, and then another integrator, like an RK integrator. Okay. So for this, again, this is going to be a small system, so just two-level systems. So the first thing that we do is set the target to dynamics. So there's a number of different backends that you can call for different things. So dynamics will be the target for doing these dynamic simulations. We're going to set the system dimensions for this two-level system and cavity. So the 0th index will correspond to the atom, and the first index will correspond to the cavity. We're going to define our operators with our operators. So the A and A dagger, we can just call these operators here. And then the way you assign what degree of freedom that they're acting on is just through this argument here. And same thing for the atom operator. So now it's operating on the 0th index, which indicates our atom. Okay. So we're just going to put all these things together. In the next lab, I'll tell you how to do like custom operators if you don't want to use standard set. And we'll also do time-dependent operators as well. So I'll just put all of that together. And then all we need to do is initialize the state of the system in CuPy arrays. And if you're not aware, CuPy is just it's basically a drop-in library that mimics NumPy, but allows you to put everything on the GPU memory. Okay, so we're going to initialize the density matrix of the qubit state, as well as the cavity state. So I just have these two arrays, and then I initialize the correct element in each array. And then I construct this initial density matrix. So I just tensor both of these states together to form the composite state. And then I call this state from from data function to construct my initial density matrix. And then I'm going to define our time steps that we want to integrate over. Okay, so now all we do is we evolve the system. So we plug in our Hamiltonian, our dimensions, our schedule, our initial state, and any observables that we want to collect. So we're going to look at the number operator for both the atom and the qubit. And then we're going to store, for this, we're not going to have any dissipation terms. And then we're going to store the intermediate results and then call this SciPy integrator. So let's run that. So that took, a couple seconds. We're running on A10 GPUs. Yeah.
Very lame question maybe, but how much flexibility do we have in defining the initial states?
You can define an arbitrary initial state in density matrix.
Okay.
Yeah, so if you want to, you could just make a giant like CUDA array as your initial state and then just manually pull it out.
Is there a limit to the dimension of the matrix? Like how many?
It's just limited by the memory of the GPU. So I want to say for like an 80 gig H100, it's something on the order of like 60,000 states in your Hilbert space, something like that. Yeah. Okay. Okay, so let's collect our results and then plot this. And, okay, so this is the picture that we expect. We have our qubit and our cavity state, and it's just swapping excitations. So that's the picture that we expect. Great. Life is good, and we can go to more advanced examples. Everyone good here? Any questions so far? Okay, so let's learn a little bit more physics. So, intuitively, the photon is being absorbed by the qubit and then, coherently re-emitted. And then we also had the flexibility to set the coupling rates in the interaction Hamiltonian. And we set this to pi/2. And so if you do a little bit of analysis on the Hamiltonian, you can derive what the oscillation rate should be or the Rabi rate. And so this is, dependent on the number of photons in the cavity. So if you, crunch all the numbers, you see that this Rabi rate is what it should be. All right, let's make this system a little bit bigger, and this brings us to our first exercise. So you're going to have to, fix the fix me sections here to make this run. So basically, let's adjust the code below to now simulate 20 photons in the cavity. So there's a couple of parts where I've indicated a fix me, and you have to just adjust the code so that this runs. So I'll give you 2 or 3 minutes for you to just do this on your own, and then we can move on from there. Are you guys running into problems or? Okay. Cool. So who wants to tell me how I should fix my code? So for the dimensions, the system dimensions, the 0, me too. Okay. And then for the first 21, good. That's a little trick. Yep. Very observant. All right. And so what should I put here for the cavity state? Good. All right. Let's evolve this. Okay. And let's collect our results. Is everyone seeing this picture? Okay, great. So yeah, same picture here, 20 photons in the cavity. It's exchanging 1 photon with the qubit. And notice a little bit more physics here. The oscillation frequency is a lot faster. So does this make sense? Is this intuitive? Someone want to give me an? Okay. Okay. So the reason for this is because the oscillation rate is proportional to the square root of the number of photons. Yeah, so if you crunch the numbers, it's about 4 times faster, which is the square root of 20-ish.
Someone's wondering, will we have access to the watch online classes after the session?
You won't have access to the GPUs, I don't think, because it's only allocated for a couple of hours.
Yeah, it's 3 of them. But the notebooks and whatnot.
They should be on GitHub somewhere. But if you just look at the CUDA-Q docs, there's a bunch of just examples already there.
What are the available integrators?
That's a great question. We can go to the docs directly and look at them. So I've linked them here. So you can see all the ones here.
Okay, and does it display also the error?
Yeah, it should. Okay, let's move on. So, okay, we did the first exercise. That's great. Let's now simulate open quantum systems with the collapse operators. So now it's pretty trivial to add dissipation terms here. So of course, we're solving the Lindblad-Master equation. So if we had no dissipation terms, we're just solving the Schrodinger equation here. But we can add dissipation terms and assign them various rates to simulate an open quantum system. All right, so basically, let's assign a dissipation term. So let's add a photon loss mechanism with a rate of 0.1. And so we use, the annihilation operator operating on the correct degree of freedom. So let's do this. So our gamma is going to be the square root of 0.1. And then notice here that in the arguments of evolve, we now have a collapse operator. And so we can add a bunch here as we so choose. And the annihilation operator, recall, I defined it as acting on the cavity. So let's go ahead and run this. Okay, so we started with 20 photons in the cavity, and then we see this an exponential decay. So this is also exactly what we expect to see. Good. Okay, so let's do something else. Let's add an additional jump operator. So let's now consider, instead of a photon loss mechanism, we're going to have a toy model of a photon excitation mechanism with a rate 0.1. So now it's your job to initialize the cavity with 1 photon, and then define the correct collapse operator to do this. So let's give it another 2 minutes for you to just fix these 2 lines of code.
Are you required to index the system by integers, or can you do it by like strings?
It's probably integers, but I haven't checked.
QDQ can be used for simulating any Hamiltonian, right? I mean, it's not limited to SC qubits. We can do CV quantum optics simulations, say to simulate nonlinear optics. So
yeah, it's not just superconducting qubits. It's kind of any arbitrary like quantum system. Any check about continuous variable? We probably don't have that yet. Okay. I think I need to restart my kernel, but that's fine. Who wants to tell me how to fix this? What? Cavity state. 1. Yep.
There's something on the screen.
That big as well. Yes, I can just start it.
So he's up.
Oh, okay. What was the issue?
He needed learn dot NVIDIA.
Oh, okay.
NVIDIA, so I'm gonna post that and have to make it a URL redirect.
Okay, so I need to change my cavity state so that we have one photon. So I'm going to change that to 1 mach. And then push in my collapse operator B here. A dagger. And how did I define this before? A dagger.
underscore.
Having A underscore G.
Oops, yeah. Oh yeah, so the dimensions.
Y was like 0. Y was 221, just like 2.3 or something like that.
Yeah. So the dimensions. So the first index here, I'm just defining as my atom, and that has 2 levels. And then the first index, I'm defining as my cavity, which has 20 photons. And the reason I need 21 is because 0 is the first level.
And then the first example, the very first example is 2, 2.
Yeah, 2 and 2. So that's just me setting up the definition of my system.
So it's 3 levels. If you added 1 to the second, so it's 20, 21 to the first one, it's 2.
In the first one, it was 2 and 2.
Then why the second one would be 20?
So it's 2 levels, but that corresponds to 0 and 1 photon. That's the yeah. Okay. All right. So it looks like I need to restart my kernel, but I'll just do that afterwards because we're in the next section. Okay. So is everyone able to get this picture here? Okay, great. All right, so we're moving right along. So now let's also add a dephasing term to the collapse operators here. And so what happens when we do that is basically we get this additional, dephasing term. So you can see that the oscillations die out a little bit faster. Okay. So let's look at many qubits coupled to the resonator now. So let's make the system a little bit bigger. So consider 6 qubits connected to our resonator. So I'll set the number of qubits to 6, and then I'm going to assign the dimensions here. So if the first dimension or the 0th dimension rather, is the cavity, I'm going to set the degrees of freedom to 2, and then, 11. I'm going to do 10 photons. I need to update this. 10 photons in the cavity and 6 qubits. So the first degree of freedom is going to have 11 assigned to it, and then 2 otherwise. And then we're going to set up our time schedule, our cavity operators, and then construct our Hamiltonian. I'm going to define my qubit interaction Hamiltonian terms, and then I'm going to assign these kind of random-ish couplings to my qubit, each qubit to the cavity, and then I'm going to also quasi-randomize the qubit energy, and we'll see what happens when we do that. Finally, we construct the Hamiltonian, and then initialize the state of the system. So create all these cavity, this excited cavity state, and then create all the qubits in the ground state, and then just tensor everything together. Okay, and I think I had this optional add like a T1 time to dissipation term for each qubit. We can implement that or not. So when we define, yeah, okay. So let's evolve it without the collapse operators, but on your own, you can add them in if you want and see what happens. And then ultimately, this is the picture that you get. So, there's many photons in the cavity. It's swapping excitations with a bunch of different qubits down at the bottom. Each one of them has like a slightly different resonant frequency, exchanging interactions with the qubit So has everyone been able to run this? Okay, good. And so it runs, in a couple of seconds. So it's still quite fast even on these 10s. So it just kind of gives you a sample of how this is just like a nice tool in your toolbox for doing these types of simulations. Okay. Okay. So that takes us to, let's take a 15-minute break and then come back at 11:30. And then what we'll do in the second lab is look at some time-dependent Hamiltonians and then learn how to do some custom operations. So you could do kind of arbitrary Hamiltonians. So everyone good? Any questions, feedback on the performance? You guys like it, dislike it, things you want? Okay. Yeah, question.
So currently we're doing so we define our pulses, we define whatever our operators here and so forth. But you have a different part of the stack that does the circuit levels.
Exactly, yeah.
Do you already have, or do you plan to have some integration where you go from the slower level? So you design a pulse, you calibrate it on like a realistic physical model, and then you make a quantum circuit and simulate RB with your randomized benchmarking with your noisy simulators.
So what you can do is in the higher level circuit model, you can define arbitrary Krauss channels for noise channels.
Mm-hmm.
So basically, if you want to have some sort of pipeline, all the pieces are in place, but we don't have a direct API call. But what you could do is do the full characterization of a full sequence, do full tomography, get a Krauss channel back, and then plug that back into noisy gate in the circuit model. Okay, great question. All right, so in this lab, we're going to do some time-dependent Hamiltonians. So this is going to be useful for things like designing pulse sequences. In the lower level APIs, there's going to be support for gradients shortly. So if you have custom codes that want to do some gradient descent or other optimization techniques for pulses, that will be possible in the future as well. But for now, let's just continue to consider these kind of simple models. So for this first example, we'll look at the Landau-Zener model. So basically, the intuition for this is you have a parameter in which you can tune its transition across a Hamiltonian. So if you have this sort of energy crossing and you have an interaction term, you get this avoided crossing. So this is a very classical, classic picture in quantum mechanics. And it turns out if you sweep across this avoided crossing, you can kind of tune the transition rate if you start in one branch and end in another branch. So if you do this, adiabatically, and you start in the ground state, you stay in the ground state, you don't cross the branches. If you do it quickly and you start in the excited state, with high probability you'll end up in the ground state. But there's this kind of intermediate regime where if you intermediately sweep across this transition, you can land in the opposite branch with a pretty well-defined probability. So what we're going to do here is going to implement these time-dependent terms. So the two things that we're going to learn here are to define a time-dependent scalar coefficient via this scalar operator. And so this is going to be useful if you just have a pulse envelope that you want to throw at an X driving term or something like that. And then we can also do this tensor callback to define custom operators. So this the Hamiltonian of this system is pretty simple. It's just this 2x2 matrix where we have these time-dependent terms on the diagonal, and then we have these coupling terms on the off diagonal. Okay, and again, this is a very small system, so you're not going to see a massive speed up on GPU, but you can easily take the pieces here, build out a much larger system, and then look at a system that will have a significant GPU speed up. Okay, so we can, of course, decompose this Hamiltonian into a sum of polys if we want to use our pre-existing operators. So, the way this looks like is you multiply your poly x by g, and then you subtract alpha t times poly z. Okay. So if you do a little bit of analysis on this Hamiltonian, you can back out the transition probability, and it's given by this exponent. That depends on your transit rate and your coupling terms. And you can also, set this to a given target transition probability, and then from that you can figure out how quickly you need to transit across this Hamiltonian to land at that target transition probability. Okay, so let's import our packages, and then we're going to again set our target to dynamics. So for circuit simulations, you just set that to either NVIDIA or there's also a CPU simulator if you just want to run it on your laptop. And then it's just the same, like Control X, whatever. Okay, so let's define our shorthand operators again. So sigma X, sigma Z, and then do some annihilation and creation operators. And so for this system, this is a very small system, so just 2 levels here. So there's just going to be 1 degree of freedom with 2 levels. Okay, so let's assign these couplings and our constants. So let's set our target transition probability to 0.75. And then we can compute what our alpha parameter should be. So that's the rate that we transit the Hamiltonian. Okay, so our Hamiltonian is defined here. So this is just the decomposition of our Hamiltonian into the sum of polys. So G times sigma X minus alpha times T times sigma Z. And so the way that we've encoded our time-dependent part is just through this scalar operator. And we use a lambda function here, so we can assign this to be any function that's dependent on T here. So for this, it's just a linear function of T, but this could be like a sine, this could be an on-flow, this could be a Gaussian, whatever you want. Okay. And so the one thing that you need to keep in mind is that the variable here in your scalar operator for your time dependence needs to match the variable that you assign in your time schedule. So that's how it knows like what variable to look for. So we're going to start our state in the ground state, assign time steps from -2 to 2. This is going to do a bunch of time steps because we're going to see that there's actually some fast dynamics happening that we need to capture. And then we're going to evolve it. So this one's going to take a little bit longer just because we have so many time steps. We have 5,000 time steps, and the simulation time will increase linearly with the number of time steps, which is to be expected because that's something that happens sequentially. Okay, so that took a couple of seconds to run. Let's collect the results and plot them. And so we see we're seeing the occupation population for the ground and the excited state, and then as we transit across the avoid crossing, these probabilities converge to the probabilities that we've kind of predicted already. Okay, so good. So now there's a second way of implementing time dependence, and it's using a custom operator. So there's 2 things that we're going to learn here. If you don't want to decompose your Hamiltonian to like a sum of polys or like other operators, you can just write it explicitly, and that's fine. And so the way that we're going to do that is with a so-called tensor callback, and by defining an elementary operator. So let's define this callback tensor here. And so we explicitly write out our Hamiltonian here. And this is a function of T. And we can do this for kind of arbitrary Hamiltonians. And then we're going to define this elementary operator, and we're going to name it. So we'll name it LZ_op, so Landau-Zener operator. It has 2 degrees of freedom, and then it'll be defined by this array, or this function, rather. Okay, so now our Hamiltonian is just going to be equal to our elementary operator. We call it from its name, and then we say we assign it to the 0th degree of freedom. And there's only 1 degree of freedom here, so there's only 1 choice there. Okay, so we set our dimensions, we set our initial state, and then our time schedule. And again, make sure that in your schedule, this T matches the same variable or the argument in our callback tensor. And then you do the exact same thing. So this is just 2 different examples of equivalent functionality. This is a little bit more flexible because you can define arbitrary Hamiltonian operators.
Is there a performance penalty to doing it one way or the other? Are they?
Not at this level, because ultimately it's constructing the same matrix and then sending it.
Down, I guess.
But that
Does the tensor thing get jitted down so that it's
not at this stage.
okay?
But it's a good question, because I don't know
So that's
if you go to like really large, like arbitrary Hamiltonians, if there's performance. I can circle back.
yeah. The reason I ask this is because this is a very big problem in QTIP. Like they do it differently because they can't just jit anything. They have to explicitly have like a Python function called each step in the
Yeah. Okay. So yeah, we get the exact same plot here. So just same functionality. All right. So now let's look at a little bit more interesting of a problem. So this is going to be a Heisenberg model with a time-varying magnetic field. So we can look at pretty large spin chains if we want to. So basically, the model here is we're going to set up this linear array of two-level systems. So this is our classic spin chain. Our Hamiltonian will give us some interaction terms between each spin, and then we're going to have a time-dependent magnetic field applied in the transverse direction. So coupled to the sigma x term of each spin. So there's a pretty common test bed for looking at like condensed matter systems. You can scale this out arbitrarily. You can add your own couplings if you want, but it's a very nice like test system to just observe some interesting dynamics. Okay, so let's set our target again, and then we're going to look at a 10 qubit spin chain. And then and we're going to initialize it in this like alternating spin up, spin down state. Okay, and so this brings us to our first exercise. I want you to define a magnetic field that is 0 until a time delay, and then switches to a field of 2, and the delay will be 2.5. So let's take like 1 minute to do this. So it just goes to show that you can have like an arbitrary like time function for these time-dependent terms, and this can be a pulse, it can be a Gaussian, it can be whatever. So basically, you can just write this simple if statement inside this function to define this time step. And so for my Heisenberg model, I'm going to set this to predominantly be like a ZZ type interaction. So the ZZ coupling is going to be the strongest, and then I'm going to have like smaller X and Y interactions. So I will construct the Hamiltonian. So just adding together all these different spin terms. I didn't make any aliases for the spin terms. I'm just using directly the spin X and spin Y operators in CUDA-Q. And then I'm going to add my magnetic field term. So this is my now scalar operator, my B field, multiplied by the spin X for each spin. Okay. So now we can execute this simulation, measuring the sigma z expectation. I think this is going to take maybe a minute, so let's just we can wait it out. Oh wait, sorry, I didn't. That run on. I don't know about that. Oh, maybe it did. That was shockingly fast. Did it complete for everyone? Oh wow, that's really fast. That was even faster than when I was testing it. Let me double check. Yeah, 10 spins. Okay, I guess so. I guess that's not that big of a system. Yeah. So in any case, it just goes to show you like, okay, so we start out in kind of a quasi eigenstate of our Hamiltonian because we start out in the alternating spin up, spin down state. So you don't see much dynamics happening here. And then as soon as I flip on the magnetic field in the transverse direction, you see, some like punch dynamics happening. So, again, just kind of a toy model, but just goes to show you that you can start programming some interesting systems. And if you have, Hamiltonians of your own, like this is like an interesting test bed to accelerate these simulations. But overall, very fast. We have some time left, and we have these GPUs booked for another, I want to say, 40 minutes. So if there's like systems that you're interested in just simulating on your own, like have at it, see what you can do. I'd be curious to see what you guys are able to come up with, and I'll kind of float around and just see what everyone is up to. I add these optional exercises, so you can play around with like having a sine function for your magnetic field. You can consider a disordered spin chain with varying couplings. You can look at different observables, so things like spin correlators or the overall magnetization. There's plenty of things that you can play around with. Or if you have Hamiltonians of your own that you want to just simulate,